Here we're going to look at an interesting identity involving Fibonacci numbers. It's called Catalan's identity. And it says that if we have Fn to be the nth Fibonacci number, Fn squared minus Fn plus r times Fn minus r equals minus 1 to the n minus r Fr squared. And this is a generalization of Cassini's identity, which we proved in a previous video. I'll link that below. And this identity down here, which is somewhere in between in terms of generalization of Cassini's identity and Catalan's identity, which we also proved in a video below. And each of those proofs relied on different methods. So Cassini's identity, we used a matrix determinant method involving a matrix exponent. This one we did just by induction. And this one we're going to use a completely different method, which involves the determinant sum property. And it's from this paper by M. Spivey. It's called Fibonacci Identities via the Determinant Sum Property, and you can find it in the College Math Journal. So we're going to need these three preparatory results in order to prove this. So the first one is about these things called generalized Fibonacci sequences. So if we define a sequence of numbers Gn, n equals 0 to infinity, by the Fibonacci recursion, in other words, we have Gn equals Gn minus 1 plus Gn minus 2, and G0 and G1 are anything, so they're free to be anything. Then Gn, the nth term, is really just the 0th term times the n minus first Fibonacci number plus the first term times the nth Fibonacci number. So that means you don't need to use the recursion at all. It's all built into this definition via the Fibonacci numbers. Then next, we're going to prove this determinant sum property, which was new to me, and I was excited to learn something new. And that says if you've got n by n matrices A, B, and C, and they're completely the same except for one row, and in that case, the kth row of C is equal to the sum of the kth rows of A and B, then we have this property that the determinant of C is equal to the determinant of A plus the determinant of B. And then finally this identity down here, which says that f sub m minus 1 times fn minus fm times fn plus 1 is minus 1 to the m fn minus m. We'll use that as well in the proof. Okay, so let's get this cleaned up and then we'll get started. Okay, so we're going to prove this thing about generalized Fibonacci numbers first, and we're going to do that by induction. And so that means we need a base case. And our base case will be the n equals 2 case, because the n equals 0 and 1 cases are really like our seeds for our sequence in the first place. Okay, so let's get started. Our base case, like I said, will be n equals 2. And notice by the recursion, we know that g sub 2 is equal to g sub 1 plus g sub 0. But notice we can rewrite that as g0 plus g1, but that is 1 times g0 plus 1 times g1. But that's the same thing as f sub 1 times g0 plus f sub 2 times g1, because we know the first Fibonacci number is 1 and the second Fibonacci number is 1. So that means our base case satisfies this rule, and we're all set to make our induction hypothesis. So we're actually going to use strong induction here. So we will suppose for all n less than k, the result holds. Great. So that's true for n equals 2, 3, 4, 5, 6, all the way up to k minus 1. It holds for all of those. And now we're going to look at the kth term, so g sub k. So by our recursion, we know that's g sub k minus 1 plus g sub k minus 2. But then, by our induction hypothesis, we can rewrite that as f sub k minus 2 times g0 plus f sub k minus 1 times g1. So just to be careful, that is rewriting this part with our induction hypothesis. Good. And now rewriting this part with our induction hypothesis will be f sub k minus 3 g0 plus f sub k minus 2 g1. Great. Now the next thing we want to do is combine like terms. So that's going to give us f sub k minus 2 plus f sub k minus 3 times g0. So that would be like combining these two. Okay? And then we also have plus f sub k minus 2 plus f sub k minus 1 g1. Okay, and that would be like combining these two. But now notice in parentheses there we have Fibonacci numbers, and those obviously satisfy the Fibonacci recursion. So this is going to be f sub k minus 1 times g0, because f sub k minus 2 and k minus 3 are the previous two terms. And then this is going to be f sub k times g1, which is exactly what we need it to be in order to finish this off. Okay, great. So now we've proven this first result. And now we're ready to move on to our next result. So we're going to prove a special case of this first involving 2x2 matrices, which is actually all we need for this case, but then we'll prove the general case as well. Okay, so proof, like I said, the 2x2 case first. And so let's go ahead and let A equal A, B, C, D, and then B needs to be equivalent to A except for one row. And actually, we can just assume that it's except for the first row, and that's because row swapping only negates the determinants. And so we can always row swap all of the matrices until this is happening in the first row. So here I'll write X, Y, C, D. So notice A and B are exactly the same except for the first row. And now C needs to have the same second row, so we'll call this CD, but then the first row is A plus X and B plus Y. So notice the first row of C is equal to the sum of the first rows of A and B. Now let's go ahead and calculate the determinant of C. So we'll just use this A plus X times D minus B plus Y times C formula, minus B plus Y times C. So notice that's going to be AD minus BC plus XD minus YC. So that's pretty easy to see. And then it's also easy to see that this guy right here is the determinant of A. And then this guy right here is the determinant of B. Great. And so that means this equation is satisfied for 2x2 matrices, where it is the first row that is undergoing this operation. And again, if it's the second row that's undergoing this operation, we can just do a row swap to all of the matrices, and we have that result immediately. Okay, so let's go ahead and clean this up, and then we'll do the n by n case. Now we're going to do the n by n case, and like we said before, without loss of generality, we can assume that this row sum thing is happening in the first row, and that's because we can always do row swapping, and we know how that affects determinants. Okay, so we're going to let A equal the matrix A1 all the way to AN, and then this block matrix below, which is given by X. And now notice X is going to be an n minus 1 by n matrix. So that's important to know. And then B will be given by B1 up to Bn in the first bit, and this block matrix down here, which is X again, because notice A, B have to be exactly the same except for a single row, and that single row will be that first row. And then finally, C is equal to A1 plus B1, dot, 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 AN plus Bn, and then this block matrix X, which is down here. Now the next thing that I want to do is set xi equal to x with the ith column removed. Great. And the reason I want to do that is because I want to use cofactor expansion for my determinant. So now notice when I expand these determinants by the first row, when I get to the ith column, I will have the ith element from the first row times the determinant of xi. So that's my purpose of doing this. Okay, fantastic. Now let's go ahead and calculate the determinant of C. And so again, like I said, from cofactor expansion, we get the sum I equals 1 to n of minus 1 to the I plus 1. So I'll let you guys look up some linear algebra facts if you need to recall this kind of stuff. There are a bunch of good playlists about linear algebra on YouTube. And then we have AI plus BI. So again, like I said, that's expanding about this first row in this ith column, and we get this AI plus BI entry here times the determinant of xi, because that's what's left when we remove that from that matrix X. Okay, but the next thing that we can do is separate this out into two sums. So that's going to be the sum I equal 1 to n of minus 1 to the I plus 1 AI determinant of xi plus the sum I equals 1 to n of minus 1 to the I plus 1 BI determinant of xi. But now, by the same reasoning, here we have the determinant of A, where here we've expanded on the ith row to have the AI entry there. And here we have the determinant of B, where we've expanded on the first row in the ith column to have BI here. So this gives us the determinant of A plus the determinant of B. Great. And that proves this second result. And we proved this in a previous video, so we won't prove it here. Okay, so we're going to use all three of those results to prove our main result. Especially, we're going to use this one mostly. So that means we need to come up with some matrices that are filled with entries that look like they come out of this identity. So the way that we'll do that is the following way. So let's go ahead and say that the matrix A0 is equal to this matrix Fn, Fn minus R, Fn, Fn minus R. So in other words, we have the first row and the second row are exactly the same in this case. And then furthermore, we'll need a matrix A1 to get us started as well. And so that will be Fn, Fn minus R, Fn plus 1, and Fn minus R plus 1. Okay, great. And now we're going to create a sequence of matrices that have these two as the seeds, and they mimic the Fibonacci sequence, except we're doing this row sum kind of thing. So in other words, we want to build the matrix AM out of the two previous matrices and this kind of row sum operation. So what will work is the following. We'll build AM by adding the second row of AM minus 1 and AM minus 2. So in other words, we have the following setup. AM equals, so this will be Fn, Fn minus R in the first row, because notice we're leaving the first row unchanged. And then down here we'll have numbers AM and BM. Second row is equal to the sum of the second row of these two. In other words, AM equals AM minus 1 plus AM minus 2, and BM equals BM minus 1 plus BM minus 2. Okay, great. So now let's look at a couple of examples before we have a guess for what the general form is. So notice we have A0 equals this, A1 equals this. So that's going to make A2 equal to Fn, Fn minus R. Recall that the first row is the same. And then we're going to add Fn with Fn plus 1. Well, we know that that's Fn plus 2 by the Fibonacci recursion. We're going to add Fn minus R with Fn minus R plus 1. So that's going to be Fn minus R plus 2, again by the Fibonacci recursion. Great. And then A3 we can calculate similarly. So that first row is going to stay the same, Fn and Fn minus R. And then the second row we'll get by adding the second row of A2 with the second row of A1. So we'll have Fn plus 2 times Fn plus 1. So that's going to be Fn plus 3, again by the Fibonacci recursion. And then finally, we'll have Fn minus r plus 2 and Fn minus r plus 1. So that's going to be Fn minus r plus 3 by the Fibonacci recursion. So that gives us a guess for the structure of AM, and that should be pretty obvious. So we have Fn, Fn minus r, and we're going to have Fn plus m here, and here we're going to have Fn minus r plus m. So what I want to do now is prove that guess by induction, but we'll have to move that to the top. So we came up with the following claim for the general form of AM. We say that it's F sub n minus r, F sub n plus m, and F sub n minus r plus m. So we're going to go ahead and prove this by induction. And notice our base case is already set because we did those examples before. Great, so let's make our induction hypothesis. So in other words, we'll suppose for m less than k, the result holds. So we're using a strong induction here. So that means that this result holds for all m from 0 to k minus 1. In particular, it holds for k minus 1 and k minus 2. So what that means is that we know that a sub k minus 1 has this form. So in other words, it's f sub n minus r, f sub n plus k minus 1, and then f sub n minus r plus k minus 1. And this holds for a sub k minus 2 as well. So let's see, that means we have Fn, Fn minus r, Fn plus k minus 2, and Fn minus r plus k minus 2. Great. And now let's recall how we form a sub k. So that's going to be equal to Fn, Fn minus r in the first row. And then the second row is made by taking the sum of the second row of those previous two matrices. So in other words, we'll add this term and this term to get this entry. But notice by the Fibonacci recursion, we know exactly what that is. That's f sub n plus k, because these are the two terms previous to that. And then also, we'll add this term and this term to get this entry. But that's f sub n minus r plus k, again because this follows the Fibonacci recursion. But that's exactly the form that we want ak to take, so we finished our proof by induction. So that means we do have this form. Okay, great. So now we're ready to clean up the board and finish it off. On the previous board, we proved that that matrix AM had the following form. So it's Fn, Fn minus r, Fn plus m, Fn minus r plus m. And then let's recall how we constructed those in the first place. They're constructed so that AM, AM minus 1, AM minus 2 are all equal, except the second row of AM is the sum of the second rows of AM minus 1 and AM minus 2. But that's fantastic because that means we can use this result in order to calculate that determinant. So let's notice that that means that the determinant of AM equals the determinant of AM minus 1 plus the determinant of AM minus 2. But now if we think about this determinant as a generalized Fibonacci sequence, then we can apply this first result. So let's maybe point that out. This is a generalized Fibonacci sequence. So what that tells us is that the determinant of AM is in fact just the determinant of A0 from this part right here. So really, this guy right here is playing the role of GM times F sub n minus 1, so F sub m minus 1, plus the determinant of A1 times f sub m. Okay, good. But let's recall what that is. So that's the determinant of Fn, Fn minus r, Fn, Fn minus r, because that's A0, plugging 0 in for m here, times f sub m minus 1, plus the determinant of Fn, Fn minus r, Fn plus 1, Fn minus r plus 1 times Fm, because that is A sub 1 plugging m equals 1 right there. Okay, now the first row here is equal to the second row here, so that tells us that that determinant is 0. And then next, we can just easily take the determinant of this to give us Fn times Fn minus r plus 1 minus Fn minus r times Fn plus 1. So like I said, that is this determinant right here, and this is multiplied by Fm. Okay, and so now we can apply our last result to this object right here. So notice these are the same with m equals n minus r. So that's good, because that means that this is going to be equal to minus 1 to the n minus r, and then f sub r. And then we have this is multiplied by f sub m. Okay, good. So now I'm going to go ahead and erase the board, and then we'll have this determinant of am is equal to this guy right here, and then we're really close to being done. Okay, so we just got to use all three of our preparatory results to prove the following. If AM was this matrix we've been working at, the determinant of AM is minus 1 to the n minus r times FR times FM. But now let's go ahead and take the determinant of AM another way just by using the definition. So notice that is going to give us the following equation. Fn times Fn minus r plus m minus Fn plus m times Fn minus r is equal to minus 1 to the n minus r Fr times Fm. But that looks a lot like our goal identity. In fact, this can be seen as some sort of generalization of our goal identity. So let's go ahead and set m equal to r, and notice that we get exactly Catalan's identity. So here we're going to have Fn and then another Fn, so that'll be Fn squared. And here we'll have Fn plus r, Fn minus r, and then over here we'll have minus 1 to the n minus r, Fr squared, which is exactly what we wanted to prove. Okay, that's a good place to stop.